Every time you pull cash from your wallet, you're holding one of the most sophisticated pieces of manufacturing on the planet, and you probably had no idea. That crisp Benjamin Franklin staring back at you from a $100 bill isn't just currency. It's a masterclass in precision engineering, a gauntlet of security features so complex that entire governments have tried and failed to replicate it, and it all begins in a place most Americans will never see. Deep inside a fortified compound in Fort Worth, Texas, something remarkable happens every single hour. Massive industrial presses thunder through their cycles, and with each rotation, 32,000 individual $100 bills emerge into existence. Not from one machine, but from an entire fleet of them, all running simultaneously, all part of a production system so tightly controlled that even the raw materials are considered contraband if they end up in the wrong hands. But here's what'll blow your mind. The security doesn't start when ink hits the surface. It starts long before that, woven into the very fabric of what you're touching. Reach into your pocket right now and feel a bill between your fingers. Notice that texture? It doesn't feel like the paper you'd feed into a printer, does it? There's a reason for that, and it's the first clue that what you're holding is almost impossible to fake. That's because it's not paper at all. What the Bureau of Engraving and Printing calls substrate is actually a textile blend, 3/4 cotton and 1/4 linen, and it comes from exactly one source on Earth. A company called Crane Currency has been manufacturing this material from their facility in Dalton, Massachusetts since 1879. Let that sink in for a second. 140 plus years, one supplier, one product. Nobody else in America is legally permitted to make it, possess it, or sell it. If you somehow got your hands on genuine currency substrate without authorization, you'd be committing a federal crime before you even thought about printing anything on it. This isn't an accident. This is strategic monopoly by design. Because if the foundation of your currency can be bought at a craft store, your entire monetary system collapses overnight. And Crane doesn't just weave cotton and linen together and call it a day. Embedded throughout every sheet are thousands of tiny synthetic fibers, red and blue, scattered randomly across the surface. Hold any bill up to the light and you'll see them. They've been there since the 1800s when Crane first used silk threads. Modern versions are synthetic, but the concept remains unchanged. Build something into the material that a bedroom counterfeiter with a scanner and an inkjet has zero chance of replicating. But those little colored threads are just the beginning. Before a single dollar sign gets printed, the substrate already contains features that would take a dedicated lab to reproduce. During the paper-making process, a thin strip of plastic gets embedded vertically into the material. Not glued on top, not stamped afterward, physically woven inside the fibers as the sheet is formed. This is the security thread, and if you hold a 5, 10, 20, 50, or 100 up to a light source, you'll see it running through like a spine. Printed on that thread in microscopic text is the denomination and the letters USA. Put that same bill under ultraviolet light and the thread comes alive. A $5 bill glows blue. A 10 glows orange. 20s glow green. 50s glow yellow. And 100s glow pink. Each thread is also positioned differently depending on the denomination, so if someone tries the old trick of bleaching a lower bill and reprinting it as a higher one, the security thread will be in the wrong location and machines will reject it instantly. Think of this like hiding a wire inside a cake while you're mixing the batter. Once it's baked, you can't move it, you can't add it, and you can't take it out without destroying the whole thing. Now, if you're holding a $100 bill, there's something else in that substrate that took over a decade to engineer. Look closely, and you'll see a blue ribbon running vertically, about 6 millimeters wide. This isn't ink. This is a woven strip embedded into the cotton-linen blend, and it contains over 1 million tiny lenses per square inch. Tilt the bill forward and backward, and you'll see miniature bells morph into the number 100. Tilt it side to side and those images shift in the opposite direction. This is called motion micro-optic technology, and it's considered the most advanced anti-counterfeiting feature on any banknote in circulation anywhere in the world. No printer, no copier, no scanner, no screen can reproduce this effect. It's a physical structure, not an image, and it exists only because Crane Currency figured out how to bake it into the paper itself. All of this happens before the Bureau of Engraving and Printing even receives the material. So when those massive rolls of substrate arrive at the facility in Fort Worth, they're already halfway to being impossible to counterfeit. And the hardest part is just getting started. The first stage of actual printing is offset, and this is where bills $5 and above get their background colors. Faint washes of peach, blue, and orange that sit behind the portraits, those aren't decorative. They're part of the detection system. The $1 bill skips this step entirely, which is why it looks and feels slightly different from everything else in circulation. The offset presses are absolute monsters. 50 feet long, 70 tons of steel and precision rollers, and they can print both sides of a sheet simultaneously at speeds reaching 10,000 sheets per hour. After every 500 prints, an operator pulls a sheet and inspects it by hand. There are no shortcuts. There is no room for error. But offset printing is just the foundation. What comes next is where counterfeiting stops being difficult and starts being physically impossible. Somewhere inside the Bureau of Engraving and Printing, a master engraver sits at a workstation with a tool called a baron, a razor-sharp hand tool used to carve metal. There are maybe a dozen people alive who can do what this engraver does. They take a soft steel plate and, working entirely by hand, carve the intricate design that will become the portrait of Benjamin Franklin. Not from a photo, not from a digital file. Line by line, groove by groove, backward and in reverse, at a microscopic level of detail. A single portrait can take months to complete. If the engraver makes a mistake 10,000 cuts in, there's no undo button. They start over. That finished engraving becomes the master die. But here's the problem. You can't use one die to print millions of bills. It would wear down almost immediately. So the Bureau had to invent a process to make perfect copies of something specifically designed to be uncopyable. Here's how they pull it off. The master die is heat-treated to harden it. Then a soft steel cylinder called a transfer roll is pressed against it under thousands of pounds of force, picking up the design in raised relief. That roll is then hardened and pressed against a soft steel printing plate, transferring the image back into recessed grooves. This process repeats to create a full plate with 32 individual note impressions. Those plates are then coated with chromium to survive what's about to happen. And just to make things even more complex, those intricate geometric patterns you see radiating behind Franklin's face, those aren't drawn by an artist. They're cut by a geometric lathe, a machine that produces mathematically generated curves so fine and so complex that no human hand could replicate them. Try to scan one. Try to photocopy it. You get distortion, blurring, moire patterns. The detail literally self-destructs when copied, and that's the entire point. Now comes the step that makes US currency feel different from anything else in your wallet. It's called intaglio printing, and this is where the magic happens. The chromium-plated steel plates, now filled with microscopically engraved grooves, are loaded into a press that applies thousands of pounds of pressure per square inch. The substrate is forced into those grooves, and ink is pulled from the recesses directly into the paper. When it comes out the other side, the ink sits raised above the surface. Run your finger across a genuine bill and you can feel the texture of Franklin's coat, the ridges in the scrollwork, the bumps in the lettering. That tactile quality is one of the easiest ways to detect a counterfeit because no consumer-grade printer or photocopier on the planet can produce it. If a bill feels flat and smooth, it's fake, period. The intaglio process runs in 2 passes. Backs first, then fronts. Each pass still operates at 10,000 sheets per hour, but speed isn't the only priority. The ink used in this stage isn't ordinary. It's formulated with magnetic particles, and each denomination has a different magnetic signature. That's how a vending machine or a bill validator can tell the difference between a 1 and 100 in a fraction of a second, and why a photocopy gets spit out immediately. But there's more hidden in that ink than magnetism. Certain sections of every bill are engineered to be visible under infrared light, while others aren't. To your naked eye, you see a complete image. To an infrared sensor, the bill looks like a barcode, alternating between visible and invisible zones. You'll never notice this feature, but every machine that's ever accepted your cash is checked for it. And here's something almost nobody realizes. Intaglio ink takes 72 hours to dry. 3 full days. Those freshly printed sheets sit in climate-controlled rooms, untouched, while the ink cures. Rush it and the whole batch smears. The entire production timeline is built around that wait. But while the ink is drying, there's more happening in the design than you'd ever see without magnification. The $100 bill in particular is loaded with microprinting G text, so small you need a jeweler's loupe to read it. The phrase United States of America is printed in tiny letters along Franklin's collar. The words USA 100 appear inside the blank space near the watermark. The number sequence 100 USA runs along the gold quill. If any of those areas look blurry or smudged, you're holding a counterfeit, because no commercial printer has the resolution to reproduce text at that scale. Then there's the bell and the inkwell. On the front of the 100 to the right of Franklin's portrait, there's a copper-colored image of the Liberty Bell inside an inkwell. Tilt the note and the bell shifts from copper to green, appearing and disappearing depending on the angle. This uses optically variable ink, the same color-shifting technology embedded in the large numeral 100 in the lower right corner. It's nearly impossible to fake without access to the same proprietary materials the Bureau uses, and those materials aren't for sale. After the intaglio ink has fully cured, the sheets move to the final printing stage, officially called COPE, Currency Over Printing Processing Equipment. Up until this point, every bill on a sheet has been identical. This is where they become unique. Serial numbers, Federal Reserve seals, Treasury seals, and the color-shifting denomination numerals all get applied in this pass. Every serial number follows a strict 11-character format. Pull out a $100 bill and look at the green serial number. The first letter indicates the series year. The second letter tells you which of the 12 Federal Reserve banks issued it, from A for Boston all the way to L for San Francisco. The 8 digits in the middle are the unique identifier. No 2 bills share this number, ever. The final letter indicates the production run within that series. Every single bill in circulation can be traced back to the exact bank that distributed it and the exact moment it was printed. For 10s, 20s, 50s, and 100s, this stage also applies the color-shifting ink to the large numeral in the lower right. Tilt a 20 or 100 and watch that number shift from copper to green. It's one more layer of security that counterfeiters struggle to replicate. Once printing is finished, every sheet enters what might be the most unforgiving quality control system in American manufacturing. The offline currency inspection system uses high-speed cameras to scan both sides of every sheet at full production speed. The system compares each note to a digital reference, checking ink density, Euler accuracy, alignment, and defects invisible to the naked eye. Any note that fails gets flagged, and here's where it gets interesting. Rejected notes are pulled and replaced with what are called star notes. Look at the serial number on a bill. If there's a star symbol next to it, that bill replaced a defective one during production. Collectors pay premiums for star notes because they're rarer than standard bills, and if you've got one sitting in your wallet, hold on to it. After inspection, the sheets are guillotine cut, first into strips, then into individual notes. Every bill is exactly 6.14 inches long and 2.61 inches wide. Those dimensions haven't changed since 1929, and they have to be exact because every ATM, vending machine, and bill counter in the country is calibrated to reject anything outside that tolerance. Finished notes are banded into straps of 100, color-coded by denomination. Blue bands for ones, violet for 20s, gold for hundreds. Straps are bundled into bricks. Bricks go onto pallets. And those pallets are loaded into armored trucks operated by companies like Brinks and Loomis, bound for one of 28 Federal Reserve cash offices scattered across the United States. Here's something most people don't understand. The Federal Reserve doesn't just print money and hand it out. It operates a constant replacement cycle. Commercial banks deposit worn and damaged currency. The Fed inspects every note, destroys the ones too degraded to circulate, and sends fresh bills back into the system. On average, the Federal Reserve moves roughly $480 million in new currency every single day. And here's the economics of it. It costs about 8 cents to produce a $1 bill. 100 costs around 14 cents. Think about that for a second. 14 cents of manufacturing costs to create an object worth $100, and that object will survive in circulation for an average of 23 years. A $1 bill, by contrast, lasts only about 6.5 years before it's too worn to use. Every year, the Federal Reserve destroys roughly 7,000 tons of shredded currency. But here's the wildest stat of all. An estimated 60 to 80% of all $100 bills ever printed are currently outside the United States. As of 2024, there are about $1.9 trillion in hundreds circulating globally. That's 82% of all U.S. currency by value in a single denomination. The 100 isn't just America's most secure note. It's the world's most trusted store of value, which also makes it the most counterfeited denomination internationally. High-quality fakes, sometimes called superdollars, have been linked to state-sponsored operations. The 2013 redesign, the one with the blue 3D ribbon, was specifically created to stay ahead of that threat. But bills are only half the story. The other half of American money doesn't roll off a printing press. It gets hammered into existence under tens of tons of force. Coin production starts with raw metal delivered in coils. These aren't small rolls. They're 13 inches wide and 1,500 feet long, the length of 4 football fields, and they get fed into blanking presses that punch out thousands of circular blanks every single minute. The leftover metal, called webbing, piles up so fast that workers literally rake it like leaves. Every scrap gets collected, shredded, and recycled. Nothing is wasted. But what those blanks are made of isn't random. Pennies are 97.5% zinc with a thin copper coating. Quarters are a copper core clad in a nickel alloy, 91.67% copper and 8.33% nickel. That composition isn't just for looks. It's why they feel different in your hand, why they sound different when they hit a counter, and why vending machines can tell them apart instantly. The U.S. Mint operates 4 facilities. Philadelphia and Denver produce coins for circulation. San Francisco handles proof coins for collectors. West Point produces bullion, gold, silver, platinum, and palladium. Between Philadelphia and Denver alone, billions of coins are struck every year. After blanking, the discs are run through an annealing furnace at 1,500 degrees Fahrenheit in an oxygen-free environment. Exposure to air at that temperature would oxidize the metal and ruin the surface, so the process happens in a sealed chamber. The blanks come out softened, ready to be shaped. Then they're dropped into a chemical bath, water mixed with citric acid and lubricants. The citric acid strips away oxidation and surface contamination. For pennies specifically, it removes copper oxide without eating through the thin copper plating. The lubricants keep the hot blanks from sticking together. After washing and drying, the blanks pass through an upsetting mill. This machine squeezes each blank through a groove slightly narrower than the blank itself, raising a thin rim around the outer edge. That rim isn't cosmetic, it's structural. Without it, the blank would flatten and spread under the force of the strike. Before the collar die was introduced in 1828, coins were wider, thinner, and difficult to stack. The rim also serves as a security feature. Inspectors check every batch to make sure the rim is present and the dimensions are exact, because an increasing number of counterfeit coins have been seized at U.S. ports in recent years. Now the blanks, officially called planchets, are ready for the most violent part of the process: striking. This is where physics meets metallurgy in spectacular fashion. Two hardened steel dies, one carrying the obverse design and one carrying the reverse, slammed together with a planchet sandwiched between them. A collar die, a steel ring with grooves machined into its interior, surrounds the planchet during the strike. On dimes and quarters, those grooves create the reeded edge you feel when you run your thumb along the rim. The force involved is staggering. Tens of tons delivered in a fraction of a second. Modern coin presses operate at over 750 strikes per minute. The Philadelphia Mint runs 63 presses. Denver operates 54. At full capacity, Philadelphia alone can produce more than 47,000 coins every single minute. The dies themselves are engineering marvels. Original designs are sculpted as oversized plaster models, sometimes several feet across. Those models are digitally scanned and reduced to coin size using a pantograph-style reduction lathe. Master hubs create master dies. Master dies create working hubs. Working hubs create working dies. And those working dies are what actually strike coins. They wear out after a few thousand strikes and get swapped out constantly. Every struck coin passes through an automated inspection system that checks weight, diameter, and visual quality. The ones that fail meet a machine with one of the best names in all of manufacturing: the Waffler. This device bends and deforms rejected coins into a waffle pattern, making them impossible to pass off as legitimate currency. The scrap metal gets sent back for recycling, though some waffled coins slip out and become collector's items. Coins that pass inspection are counted by machine, weighed for accuracy, and packed into heavy canvas bags. Those bags are so dense they can only be moved by forklift. They're shipped to Federal Reserve banks and distributed to commercial banks across the country. And here's where the economics get weird. The penny costs 3.07 cents to manufacture. The nickel costs 11.18 cents. Both have cost more to produce than their face value every single year since 2006. It's been a money-losing operation for nearly 2 decades. Dimes and quarters, on the other hand, are profit machines. A quarter costs about 9.5 cents to make, giving the government over 15 cents per coin in seigniorage, the difference between production cost and face value. The 50-state quarters program, which ran from 1999 to 2008, generated an estimated $6.3 billion in profit, largely because millions of Americans collected the coins instead of spending them, effectively removing them from circulation and forcing the mint to produce even more. In late 2025, the mint officially stopped producing pennies for circulation. They're still legal tender. They're still valid. You'll still find them in your couch cushions and at the bottom of your backpack. But the assembly lines went quiet. So the next time you're standing in line and you hand over a $100 bill or you're digging through your pocket for a quarter, take a second to appreciate what you're actually holding. 14 cents to manufacture, 23 years of lifespan, and more than 1 million micro lenses embedded in cotton just to make sure nobody on the planet can replicate it. That $100 bill isn't just money. It's a weapon in an ongoing war against counterfeiting, and every single one of those features exists because someone somewhere tried to fake it and got close enough to scare the Treasury Department into action. If you found this deep dive into how money is made fascinating, and you want to see more breakdowns of the invisible systems running the world around you, go ahead and hit that like button and